Okay, so we have the promise of the knowledge of everything, at least everything within a certain category. And we saw how we could see quantized energy last time and structure related to dynamics, how nuclei vibrate and how it's different for heavier atoms. Today we're going to look again at a different kind of dynamics and also at bonding. So in the one-dimensional world, this is the payoff. We have to go to the three-dimensional world. Okay, so you did problem sets for today and you're now familiar with things like this. What do you know about the blue curve and the red curve here? Anybody got a suggestion of what to do or what they tell you about what the true solution is? Yeah, Angela?
It looks like the true solution is somewhere between them.
I can't hear very well.
It looks like the true solution will be somewhere between them. Because it looks
Yeah,
like
the true solution should be between them. The red one is too hot and the blue one is too cold, right? So they'll be in between them. There'll be one that'll just come back down to the baseline for Hooke's law. Now the problem is that this isn't Hooke's law because I didn't show you the whole picture. It's in fact a double minimum, right? And those are both true solutions, okay? So the correct single minimum energy would lie between those two. But for the double minimum, there's a solution that's lower in energy and a solution that's higher in energy. Now, what would happen if we moved the wells further apart? Here you see the separation of the two wells is 0.6 angstroms. Suppose we moved it apart to be 1.3 angstroms, right? Now we have blue and red solutions. But now you notice it's the blue solution or the red solution. They're the same in the left. And they're both the same as the single minimum. So if you get the wells far enough apart, they look like single minima with respect to their wave function. Okay? Now, closer wells, if we move the wells closer together, we get a lower minimum energy than for the single well solution. Okay? And we get a higher energy for the next higher one. But they both look like the single minimum, but they both started when the wells were far apart, looking like the single minimum solution, one with no nodes, one with one node. When the wells were far apart, they had the same energy as the single minimum. But when the wells come together, the one with no nodes has less curvature, less kinetic energy, and is lower energy than the single minimum. And the other one has one node, more curvature than the single minimum, and a higher energy. That is to say, there's a splitting between the energy of these two. If the wells are far apart, they're the same as the single minimum, both of them. The no nodes and the one node solution are the same as the single minimum. But if you bring them together, the no nodes is lower in energy and the one node is higher in energy. So the energies split about the original single minimum structure. Now that's really important because that's what makes bonds, right? So if we have two atoms or one-dimensional wells far apart, say A and B, right? And we get a solution in A and a solution in B. And if we want the solution for the whole thing, we just put them together that way, right? No nodes. Or we could flip B upside down, multiply it by -1, add them together then, and we get one node. But they have the same energy as the single ones would do, right? But if we bring them together, the energy gets lower, less curvature, right? And that consists or gives rise to a stabilization of the particle. The particle is more stable when the wells are closer together, right? What would you call that? That's a bond. The energy is lower when they're close together. So that holds A and B together because the energy of the particle is lower when the wells are close together. So that's bonding. And part and parcel of this, the flip side of this, is that you have this wave function which is higher. What will we call that? Antibonding. So you get combination, a bonding and an anti-bonding combination, because the kinetic energy changes when the wells come closer together. You get one that's less curved, one that's more curved. Okay, now that's bonding. How about dynamics? Well, suppose we have this double minimum, and suppose we put a particle in and stop it there. So it has zero, that's our zero of energy, and then we're going to let it go. What will it do if it's classical? It'll roll back and forth, right? Bingo, let it go. Roll across to the same height, and roll back again, and then roll across again to the same height. With no friction, it goes on forever, right? But here's what happens special in real quantum mechanical systems. Oops, that went too far. And now it's going to roll back and forth in the right. But every once in a while, it goes across from one well to the other. Now, this is called tunneling for obvious reasons, right? But the word tunneling, I hate. It's one of my pet peeves. It's misleading and mischievous because it suggests there's something weird about the potential energy, right? That you can tunnel through and have a potential energy lower than you would have guessed from the potential energy curve. But that's not right. What happens is, when it's in the middle, you have negative kinetic energy. You have the potential energy that the curve shows, but the kinetic energy is negative. The potential energy can be higher than the total. And this happens in every bonded wave function, as you saw in your problem set, that the waves always go out into that forbidden region of negative kinetic energy where they curve away from the baseline. So there's the forbidden region, out to the left, to the right, and also in the middle for that energy, right? And what really happens is that you go to negative kinetic energy and high positive energy to get over that hump, and then you get across to the other side. Now, how often does that happen? It turns out that the time to get from one well to the other, which I won't be able to prove to you because it requires time-dependent quantum mechanics, and we're talking about time-independent quantum mechanics. But let me just tell you that the answer is if you know the energy difference between the blue and the red, that the rate of getting across is 5 times 10 to the minus 14th seconds divided by whatever that energy is expressed in kilocalories per mole, right? This is just an assertion, and it's based on time-dependent quantum mechanics. It's true, but I'm not telling you why, so you won't be satisfied, I hope, okay? So the energy difference here is 1.4 kilocalories per mole. So how rapidly does a particle then get from if it started out in the left, how long do you have to wait on average until it's in the right one? You have to wait 5 times 10 to the minus 14th divided by 1.4, which means about 4 times 10 to the minus 14th seconds it takes to, quote, tunnel. Although it really doesn't bore through, it goes over with negative kinetic energy. Okay, so there's something else about dynamics, and we're hoping soon to get to reactivity. It'll come after the exam, after we talk about atoms and molecules. So now it looks like we're in a pretty powerful position, at least with respect to one dimension, because with this Erwin program, we can find satisfactory wave functions for any complicated potential. We can make it anything we look like and just follow the recipe, find out allowed energies, shapes of wave functions, probability, density, rates of tunneling, all this kind of stuff. And we can rank all the wave functions by their energy or their curvature, the number of nodes they have. Here's an unsatisfactory wave function. What do you notice that's bad about it? Just to show that you've learned something, yeah.
It doesn't start at the baseline.
It doesn't start at the baseline on the left. How about on the right? Does it look okay on the right? Lucas?
Is it continue going
I crosses the baseline in the forbidden region. Right? If it crosses the baseline while curving away, it's bound to go to negative infinity or positive infinity if it crosses in the other direction, right? And on the left, because it didn't get to the baseline when it became flat, it's going to keep curving and go up to infinity. So you've internalized a lot of this stuff now. Congratulations on doing well on the problem set. Okay, so that was a bad one. Okay, so it looks like we're in pretty good shape. We even can handle multiple minima and understand tunneling and so on. The unfortunate thing is this curve tracing recipe doesn't work if you have more dimensions. Remember, the reason it would work is if you knew the potential and the kinetic energy, the potential and the total energy, then you knew the kinetic energy, and you could assign it to curvature, right? But if you have two dimensions, then there are two different curvatures you could assign it to, and you don't know how much to put in each of them. So it's no longer such a clear-cut problem if you have more dimensions, especially 3n dimensions. So when there are many curvatures, it's not clear how to partition the kinetic energy. But Schrödinger had no trouble. The Schrödinger equation is what's called a differential equation. It involves derivatives, right? And you haven't, how many people have had differential equations? Okay, maybe a fifth of you, I guess, or fewer, right? So the rest of you are feeling, gee, I wish I knew differential equations because then I could do this. But Schrödinger, but you don't have to because people already have done it. You don't have to develop this from ground zero, right? And Schrödinger didn't solve the differential equations either, right? He knew what the solutions were because people had been studying them forever. And the reason they studied it was because of studying acoustic waves and light also. And Chladni is the guy who originated this. And here we have a book by Chladni called Acoustics. I got it out of the library. This is, in fact, the new unchanged edition from 1830. The original edition was something like 1805 or something like that. Actually, we'll see it here, I think. There's Chladni, Ernst Lawrence Friedrich Chladni. And this is the title page of that book, Acoustics. The original one was 1803. Ours is 1830. Okay, now what he did was take plates of different, or he also did violin strings and timpani heads and things like that. He was interested in all kinds of acoustics. So, but the particular experiment we're interested in was he would take a plate and suspend it in the middle and touch it in different places while he was bowing it with a violin bow to make it vibrate. Okay, so you bow it in different places, and he put sand on the surface of this thing to see what patterns would be formed when the thing vibrated. You know, this is why violins have the shape they have, is so that they'll vibrate in certain ways when you bow to make them vibrate. And the sand collects where the plate isn't vibrating, because when it's vibrating, it shakes it away. So you get a picture of the pattern of vibration. Now, I'm going to try to show this to you. But it might not work, and just in case, I can go to the web. So what we have here is I can't play a violin, but as you know, I can play a bell. In fact, I can play a bell in several ways. Not only that, I can do it this way too. Oops. Shoot. Now, that's not a very pleasing sound. Why? Why is it, what's noise? I'm not very good at playing the bell. Why does dry ice make a bell ring? This was discovered in London by an ice cream vendor who had a bell on his cart. And he asked a physics teacher, a woman in London, why his bell rang when the dry ice from his ice cream hit it. See, when you touch metal like that, it gives heat to the dry ice, which causes it to give off a pressure of gas. But when it gives off the pressure and the metal moves away, then heat's not being transferred, so it stops. So you get rapid pulses of CO2, which make the thing ring. But depending on how you touch it, you get noise because there are many different patterns of vibration at different frequencies that are being generated. If I could do it just right, I would generate just one pure tone, and then you'd say, what a great player of bells he is. Okay, now I'm going to try this, and I may fail in the same way, to do an experiment like Chladni's, but instead of using a violin bow, I'm going to put sand on here. Instead of using a violin bow, I'm going to use this piece of dry ice. Let's see, like that. Okay, and I have to, if I just touch it, it won't do anything because I'll be touching sand and I won't get heat transfer. So I have to brush a little bit to get a clean part of the brass. And then let's see what happens here. Now I'm doing the same thing I did with the bell, right? It's just noise. But let me try someplace else here. This is an empirical science. Right, let's try someplace else here. Spread some around you. If you're lucky, this is really great. Hear that pure one? Maybe it's not sharp enough. We don't want to spend too much time doing this. I want to try one more, and then you can go to the website and see a much better one. Once I played just the lost chord, you know, a really beautiful tone, and it's on, you can see it on the web. I'm trying to find where and how hard to touch so that I get a really pure tone. Well, you can get patterns that way. Okay, you can get much prettier patterns and prettier tones than I'm able to coax out of the thing right now. And you can look at it on the web to see it. Okay, turn that off. Oops, wrong one. Okay, that has to cool down, but I'll put the lecture over there temporarily. Laptop. Yeah, there we go. Okay, once this cools down, we'll get back there, sorry. Okay, so these are some crude Chladni figures that I've made in the past. 3 rings. 2 rings with a line through the middle, vertically. That's the one we just made now, I think, isn't it? Isn't it the same number? A ring and 3 diameters. And there's a circle and 4 diameters. I actually made that in class last year. Okay, these are ones that Chladni did back in the late 18th century, taken from that book, right? And here, the first ones are just diameters, And the next ones are rings together with a certain number of diameters, or 2 or more rings. Now, let's see what that picture means. Below, you see a vertical diameter and 2 rings. On top, you see color-coded as to whether the plane, at an instant of vibration, whether it's toward you or away from you as it's vibrating. That's the pattern of it. Because those lines don't move, but either side of a line, one side moves up, the other side moves down. Okay? Or you could look at it this way. The dotted patterns, the circles and the line, don't move as the rest of the thing deforms. This would be like a drum head on a timpani. Got the idea? So that's the pattern of motion. Now, Chladni was interested in sound, right? So he found what pitch each of these different patterns corresponded to. So this table shows the number of diameter that are nodes, the number of circular nodes, and what pitch it corresponds to. And the little lines mean it's a little sharp or a little flat, something like that. For example, the one with 2 diameters and no rings is the pitch C. Got the idea? So then he tried to figure out if there's a mathematical relationship among these things. Those were 47 patterns that he observed there. So here he says the pitch relationships agree approximately with the squares of the following numbers. So how many diameters, how many circles? And what he sees is if the frequency is roughly the number of diameter nodes plus twice the number of circular nodes squared. This is his empirical observation. So for example, you could have 2 diameters or 1 circle. Both would give the number 2, which you then square, right, to get something proportional to the frequency, right? So there are 2 different ways to get the same pitch. Okay, that's what's crucial, either rings or lines. Or you can have a combination of rings and lines. So for higher frequencies, you can get more and more combinations that give the same pitch. For example, the number 8, you can have 4 circles, 3 circles and 2 lines, 2 circles and 4 lines, a circle and 6 lines, or 8 lines. All of them give the number 8 and all give the same pitch, at least approximately. Okay? So this is what but the lesson we want to take is that there are different ways of getting the same frequency by combinations of these nodes. Okay, now, Chladni didn't solve his problem mathematically about how plates or strings or whatever vibrate, but there were great mathematicians working on this, like Bernoulli, Lagrange, Euler, who not only made a communist Germany stamp, he also made a Swiss 10-franc note. Okay? Okay, so the size for 1-electron atoms, now we're going from 1 dimension into 3 dimensions for a real atom, electron in an atom. So for 1-electron atom, there are going to be 3 variables, x, y, z for the electron, and the solutions, the waves we're going to get, involve what are called spherical harmonics. And they're 3D analogs of Chladni's 2D figures. These mathematicians could work in 3 dimensions as well as 2. Okay, so a 3-dimensional H-atom wave function, psi, can be written as a product of 3 functions, an R function, a theta function, and a phi function. And these were available from other old-time mathematicians. The R function is called the associated Laguerre function, and it's named for Edmond Laguerre. And the theta function is called the normalized associated Legendre polynomial, after Adrien Marie Legendre. Okay? Now, here are the solutions. Schrödinger didn't find these. He just looked them up. These guys had already done it from acoustics for 3-dimensional things vibrating, right? So so here's a table that you can use the same way Schrödinger would have used it to find out what wave functions for electrons in 1-electron atoms actually look like. In all your books, you've seen pictures of these things, but you've never seen, my guess is, you've never seen the real thing. And you should wonder, Are these pictures that people have shown me right? I'm going to get the center projector on again if I can. Yeah, okay. Now, how do you understand? This looks pretty complicated, this table, and in a sense it is. But if you look at it the right way, it's really pretty simple. It relates to the position of an electron, shown on the right there, relative to the nucleus. And there's only one electron. It's a one-electron atom. Otherwise, we have more dimensions, right? But the nucleus can have any charge you want it to. So it's a one-electron atom of any nuclear charge. And we have the coordinates, x, y, z. And we have a potential. With the potential, what's the potential law that's given to us? Whose law? Coulomb's law. So it's 1 over r squared. And how do you write r squared? R squared is x squared plus y squared plus z squared, right? Everybody know that? Everybody know that? Good, nod, yes, good, okay, we're on the same page here. Okay, but that's pretty complicated function, right? So the equations that involve that are going to be really, really complicated. But there's a clever way to get around this. Do you know what that way is? What's the clever way of getting around this? The clever way of getting around it is to change the coordinates, the system that you're using, to one that's more natural for the problem. And the one that's natural for the problem is spherical polar coordinates. So the 3 dimensions are r, the distance, and theta, the angle down from the z-axis, and phi, the angle rotated around from the x-axis. Well, you can define it any way you want to. This is the way it's defined for these purposes, okay? Now, so that simplifies the expression for potential enormously. Instead of being 1 over the square root of x squared plus y squared over c squared, it's 1 over r, or some constant over r, okay? And what that means is, and this is the mathematical payoff, that the wave function can be written as a product of 3 functions, each of which is the function of only one variable. Instead of having x squared, y squared, z squared all mixed together in this complicated function, you have a function only of r, a function only of theta, and a function only of phi, and you multiply them together, and you get the solution to the Schrödinger equation for a one-electron atom. Now, this table gives you those functions, the r function, the theta function, and the phi function. It's like a restaurant where you get to choose one from column A, one from column B, one from column C, right? Here's your appetizer, your main course, and your dessert, right? So you choose one of these, one of these, one of these, multiply them together, and you have the true function, right? Now, they look very, very complicated. You can't choose any combination you want to. Once you've chosen one, once you've chosen your appetizer, you can only have certain main courses. And once you've chosen that, you can only have certain desserts to get solutions, right? This is what these mathematicians had all figured out, okay? And so how do we go about doing it? Well, we can name the psi we're going to get by a nickname, like 1s or 2px or something like that. But you can also name it by the numbers that name these individual functions. And those are n, l, and m, which I think you've encountered before probably. So let's make a try at it. No, actually, notice something about the complicated form of the functions. First, every one of them has z over a0 to the 3/2 power. Z is the nuclear charge. A0 is a unit of length of half an angstrom about. Okay, so to the 3/2 power, that's pretty weird. But remember what you're going to do with the wave function? What do you do with wave functions other than find energy? Get probability density. And what do you do to do that, Sam?
Square it.
You square it. So when you square it, it's going to be z over a0 cubed. Right, when you square it. Everybody with me on that? Okay, so what that means is you're going to get units that are z cubed per unit volume, because remember A0 is a distance. So A0 cubed is a volume. So it's going to get a number. The nuclear charge is a number. Z, the atomic number, is a number. So it's going to get a number per unit volume, which is the right units to have for probability density. What is it per unit volume? Okay? So this is just the bit that scales it right so that you get the right density and the right units. Okay, so Z, so you can drop that out. That's not something very fundamentally interesting. Okay, let's try making up a 1s orbital. Where do you start? Can somebody tell me where to choose? It's not hard. They're labeled with red, right? If you want 1s, you choose the top one. Okay, and now if you've done that, n is 1 and L is 0. So when you come to the next one, L has to be 0. Now M can be either 0 or 1. Oh no, actually, wait a second. If it's 1, no, if L is 0, then M has to be 0, it says in the second column. Does everybody see that? You see up at the top? It says if L is 0, then M can be 0. LM, okay? If for M, pardon me, to be non-zero, like here, you have to have an L that's greater than 0, okay? So to get a solution, if you chose N1 and L had to be 0, because remember, that's the only choice here, you can't have a higher L, then M is also going to be 0. So you got to take this times this times this. Okay? Now, how complicated are those functions? Okay, square root of 2 over 2. That's just a constant. That's a nothing function. Or 1 over the square root of 2 pi. Right? Big deal. Why do you have these constants in there? Why do you care what constant you multiply the wave function by? For what purpose?
Normalization.
For normalization, right? If you want to get but if all you want is the shape, forget constants. So what's the real working part of the 1s wave function? What's the part that varies? We have here this z over a0 to the 3 halves, forget that. 2, forget that. Square root of 2 over 2, forget that. In fact, the 2's would cancel. Square root of 2 here would cancel that square root of 2, so it's 1 over the square root of pi times this, times what? E to the minus rho over 2. That's the real working part of it, right? When you square it, what are you going to get from e to the minus rho over 2? What's e to the minus rho over 2 squared? Yeah, Alex? E to the minus rho. Okay, so the probability density is going to be e to the minus rho times a constant. Okay, so here we got it. It's a constant times e to the minus rho over 2. When we square it, it's e to the minus rho. Now, there's something interesting. So, there are two things that are interesting here. One, we wanted to get a function of r, theta, and phi, but we don't have r in it, right? We have rho instead. Why do we substitute r by rho? There's a good reason for that. Rho is defined, which is indeed the Greek version of r is rho, okay? It's defined as r times a constant. The constant is twice the atomic number divided by n, the quantum level n, times that distance a0. And why do you do it that way? It's because if you do it that way, then the same rho works no matter what the nuclear charge is and no matter what n is. So you get the same, so it makes the table very compact, right? Because you use the same thing no matter what atom you're dealing with, right? If you work in units of rho rather than r, that is scale r to take into account the fact that you can have various nuclear charges. Okay, allows using the same e to the minus rho over 2 for any nuclear charge z and any n. And notice every one of these has e to the minus rho over 2 on it. Now, why does that make sense? Why is it no surprise that these things have e to the minus r? Have we ever seen that before? E to the minus x as a wave function? What kind of wave function does it, what does that mean when you have e to the minus r? That's a constant negative kinetic energy. Constant negative kinetic energy, which is going to be the situation for any nucleus and an electron. Once the electron gets pretty far away, the energy stops changing, right? So the potential energy is constant, the kinetic energy is constant, right? If the electron is bound to the nucleus, that means it can't just fly off to infinity, right? So it's below the ultimate potential energy. Then you have constant negative kinetic energy when you're far from the nucleus, right? So e to the minus rho. So it doesn't surprise you that every one of these has e to the minus rho in it. Okay, now let's just look at this scaling quickly. Okay, so here's e to the minus rho and rho as a function of rho. Okay, now suppose so we can rearrange this. R is that. If we want to make a new plot which has the horizontal axis being r, being distance instead of rho. Okay, now so r for a hydrogen atom, the 1s orbital of a hydrogen atom, is 0.53. So n is 1, a0 is half an angstrom, z is 1, so it's 0.53 over 2 times rho. So we could just put a new scale on there. So here's half an angstrom for a hydrogen. Here's 1 angstrom for a hydrogen. Everybody with me on this so far? How I did that? Right? I just went through and found out for any given rho here that I already had 1, 2, 3, 4, 5, e to the minus rho. For any given rho, what would the r be if I were talking about a hydrogen atom? Okay, and I just put a new scale on there. Now, if I were talking about a carbon atom, which has a nuclear charge of +6, right? Then this number z is going to be much bigger. It's going to be 6 times as big. What effect will that have on the scale? So suppose we're at 5 for rho, right? Instead of dividing by 1 for z here, I'm going to be dividing by 6. So I'm going to get much shorter distances, real distances rather than r, rather than rho, I mean, right? Does that surprise you that the function is going to squash in if I have a +6 nuclear charge? Does it surprise you or not? It's what you expect. A bigger charge is going to suck the electrons in more. Okay? So if I do it for carbon, I get 0.53 over 12 instead of 0.53 over 2. And the scale is going to look like that. Instead of this being 0.5 here for hydrogen, it's 0.1, right? So then if I squash it in so that they're on the same scale, those are different angstrom scales for carbon and hydrogen. If I make them the same scale, the bigger nuclear charge sucks the 1s function in by a factor of 6, and it looks like that. But now, of course, if I want the normalized function, it's got to be higher, right? So that the total area is the same. I have the squared function here, e to the minus rho. Remember, the wave function was e to the minus rho over 2. The density is e to the minus rho. To get the same thing, I'm going to have to multiply that by 6, so it's going to look like that. So that's how the radial distribution, probability density distribution, looks different for a 1-electron atom with a +1 or a +6 nuclear charge. Carbon holds its core electrons in much more tightly than hydrogen does. No big surprise there. Okay. So here's something to think about. How would it differ if instead of talking about the 1s orbital of carbon, I was talking about the 2s orbital of carbon, right? Now, rho is going to be different. The n here instead of 1 is going to be 2. So it's going to change the scale by a factor of 2. So the 2s are further out. Okay, so for Wednesday, I want you to do these problems. You can do them in groups if you want to. Some about Chladni figures, and then some things about energy and some atomic orbital problems. Okay. Now, we already looked at the 1s. Let's look at some other atomic orbitals. Incidentally, this function, the Coulombic function, is simpler in 3 dimensions than it is in 1 dimension. It was that complicated thing in 1 dimension. Remember that had the cusp on it? It was a really complicated function, but it's really simple in 3 dimensions. It's just exponential in r. How does it vary with theta? As you come down from the axis, how does the wave function vary, the 1s? What does it say? How does it depend on theta? It doesn't. How does it depend on phi? It doesn't. So what shape does it have? It's spherically symmetric. It depends only on r. And the dependence on r is as easy as pi. It's just e to the minus r. Or rho, depends on what units you measure r in. Okay, now let's look at 2s. Now tell me what to do. How do I write a 2s function from this table? First I have to choose the appetizer. Where do I go? Second one down is 2s. Okay, so I take this one, and now 2s, that means L is 0, right? So where do I go? What direction do I go? Here, right? And then what direction do I go? Straight across, because m is 0. Okay? So there's 2s, multiply those together. Now, what's interesting? There are a bunch of constants that are going to make it normalized. So that's a constant, just like they were before. This is a constant, that's a constant. But this part is interesting. 2 minus rho times e to the minus rho over 2. That's the function that we're interested in. 2 minus rho times e to the minus rho over 2. That has an interesting thing. What happens when rho has the value 2? It has the e to the minus rho over 2. That's just decaying. So all of them have that. But how about the 2 minus rho? That gives an interesting thing. What happened? What's its value when rho is 2? 0. So there's a node. What shape is the node? Is it a point? Is it a line? Is it a wiggly thing? It's a sphere. It's spherically symmetric again. So there's a spherical node. So inside, and at a node, the wave function changes sign. So inside it's one sign, outside it's the opposite sign. Okay? Now, how about a 2pz orbital? So where are we going to go? 2p, we'll start with this. And for pz, we do this one. And for z, we do this one. So it's this times this times this. I think I have that circled here. Let's see. Yeah. This time, is this one interesting? No. Is this one interesting? What part of it's interesting? Cos theta is interesting, right? That's real variation. And what part's interesting here? It's rho times e to the minus rho over 2. Okay, so it's some constant times rho times the cosine of theta times e to the minus rho over 2. You always have the e minus rho over 2, forget that. It just means it decays as you go out. Now, rho times cosine of theta, what does that mean? Rho, which is this distance, times the cosine of theta. What is that? Russell? It's z. So I can simplify this a lot if I mix my metaphors between polar and Cartesian coordinates. It's z times e to the minus rho over 2. That's the 2pz orbital. Now, can you guess what the 2px and the 2py look like? Can somebody guess the 2py? Josh?
If you replace x with...
Replace what?
Replace z with x.
Replace z with x, you get the 2px orbital. Replace z with y, you get the 2py orbital. Pretty straightforward functions. Now, how about, you've seen pictures of p orbitals. It's interesting, now that you know what the functions look like, it's interesting to go back to the pictures you've seen and see what they mean. How do they relate to the actual formula? So you could plot, remember it's 3 parts, an r function, a theta function, a phi function. We could look at each of those functions separately if we wanted to. Okay? We've been talking about the R function, how it would behave. But how would the theta function behave in this cosine theta? So we'll do a polar plot that shows the value of cosine theta as a function of theta. Everybody with me? Okay, so what is it when theta is 0? What's cosine of theta? 1. Okay, so there it is, and we'll put a point there. Okay? Now let's go to plus and minus 30 degrees. Cosine is 0.86, and we'll put points there. And let's go to 45 degrees. It's square root of 2, square root of a half, 0.71. Put points there. At 60 degrees, it's a half. Put points there. What is it if it's 0? If it's 90 degrees, pardon me. If it's 90 degrees, cosine is 0. So we got a point at the origin, right? So you can see what the shape is. What if you go the other direction? What if you go beyond 90 degrees? What happens to cosine? Changes sign. So you got another circle that's negative on the other side. So there's a p orbital. But I'm not showing the whole p orbital, right? I'm just showing how the angular part varies. So you've seen pictures like that of p orbitals, which is the theta function. Or I could square it in order to look at probability density as a function of theta, right? And it would look like that. So you've seen pictures more or less like that. Or I could make a picture like that, which is a contour plot showing how big it is on a slice through the nucleus, right? So it's rho times e to the minus rho over 2 times cosine of theta. That multiplied by a constant is the wave function. Okay, so you can see it's positive up the top, negative at the bottom. And let's look at it a little bit. So, and notice it doesn't depend on phi, the angle of rotation around here. So we can take that picture and rotate it to give a three-dimensional dumbbell. Okay? We're just looking at one slice here in order to be explicit. Okay, now, so there's a certain point there that has a certain rho and a certain theta, and therefore it has a certain value. Now, let's find the maximum from of that function. Okay, so first, it depends on cosine theta. What will theta be in order for this to be maximum? 0. So it has to be along the axis. Okay? Now, so theta has to be equal to 0. Okay. Now, how do we find where it's going to be maximum with respect to rho? We take the derivative with respect to rho, set it equal to 0. So that's this, or simplified that, or simplified that. Rho equals 2. So there's the maximum. And we could find what if we put the constants in, we could find the true probability density anywhere, right? Just plug in theta, plug in rho, and square it, multiply it by the constant. That's the electron density at the point you're talking about. Now, or you could have a computer do it for you, and that's where we're indebted to Dean Dowger, who's a physicist. He went to Occidental College and actually wrote this program while he was there, but then he got a PhD at UCLA in physics. And he wrote this for physicists, but we'll use it. Okay, here's a picture of Dean Dowger. He also juggles. And here's a picture of him at an Apple developer conference, and he's juggling, the guy on the left there. He also drops one of the pins. He's not perfect. Okay. So this is his program. He's at the Apple Developer Conference. It works only on an Apple. So if you don't have an Apple, borrow somebody's Apple to look at the program, because it's really fun. This is the screen of the program, and I don't have time to take you through it now, but you should try it. So look at the PowerPoint at this in the next few slides to learn what all the different information is that's being given here and the kinds of questions you can ask. There's a 1s orbital, right? And it's as if the electron were really colored, and it's a picture of how it would actually look if you could see electron density. But all, of course, he's done is use fancy computer graphics to plot the square of the wave function, right? But it's a really nice program. We'll talk about this a little more next time.